Good morning, students. Till now, we have studied continuity and differentiability thoroughly. Today, I will going to start a new topic, mean value theorem. In this chapter, we mainly discuss two theorem of differential calculus, Rolle's theorem and Lagrange mean value theorem, which is also known as first mean value theorem. To understand this chapter, you are required to know how to check continuity and differentiability of a function at a point and how to use different properties of continuity and differentiability and ordinary differentiation. So, first we start Rolle's theorem. Here the statement of Rolle's theorem is, let f is a function from closed interval ab to R, that is, f is a real valued function defined in closed interval ab. Here closed interval ab be the domain of the function, such that it is continuous in closed interval ab, differentiable in open interval ab, and fa equal to fb. Then there exists at least one or some x equal to c belongs to open interval AB such that f dash c equal to 0. Here, Rolle's theorem is stated in two parts. First part is condition or hypothesis of Rolle's theorem, continuous in closed interval, differentiable in open interval, and functional value at end point A and B are equal. And second part is conclusion. There exists at least one or some value of x in open interval AB such that f dash c equal to 0. Means any function which satisfy these three conditions, then there must its derivative at a point in open interval vanish. We explain it by different graphs. Here, graph of function y equal to fx, and we take interval a to b, and corresponding point on the curve is point A, point B having coordinate a fa, and point B coordinate b fb. Function is continuous from a to b, differentiable from a to b, and here c is a point, corresponding point on the curve cfc. Here tangent is parallel to x-axis. In second figure, from a to b, we have a graph y equal to fx. From this point to this point, function is continuous. From a to b, there is no corner point, so differentiable, and at end point this height and this height, that is fa equal to fb, are equal. Here fa equal to fb are equal. These three conditions fulfill. Then between a and b, we have one or more, at least one. Here c1, c2, c3, tangent is parallel to x-axis. Third situation, again curve y equal to fx, from a to b, function is continuous, and curve is smooth at each point, so differentiable, and fa equal to fb. Here value of function at a equal to 0, value of function at b fb equal to 0, so fa equal to fb. Then open interval, in between open interval AB, we have 2 points C1 and C2 where tangent is parallel to x-axis. Geometrically, This theorem can be stated as f is a real valued function is closed interval ab such that there is no break on the curve from point A to point B. Second condition, corresponding to differentiability, it is possible to draw unique tangent at each point in open interval AB to the curve. Third, functional value at end point, that is ordinates, are equal. This is the geometrical meaning of condition. Then there exists at least one or some point x, say it C, belongs to open interval AB, where derivative vanishes, that is tangent is parallel to x-axis. We know geometrical meaning of differentiability. F dash C means slope of tangent at a point x equal to C to the curve. So f dash C equal to 0 means slope of tangent at the point corresponding to C to the curve is either parallel to x-axis or x-axis. In this case, tangent is parallel to x-axis, tangent is parallel to x-axis, here tangent is parallel to x-axis. An alternative explanation of Rawls theorem called algebraic meaning of Rawls theorem. Here the statement is, between any two roots of a polynomial equation fx equal to 0, there is always a root of its derivative f dash x equal to 0. Between any two roots of a polynomial equation, there is always a root of its derivative. Let fx equal to 0 is a polynomial equation. Here fx is a polynomial and its roots be a and b. Since polynomial function is continuous and differentiable everywhere, every polynomial function everywhere continuous and differentiable, so it is continuous in any given interval or closed interval AB, differentiable in open interval AB, and fa equal to fb. Here a and b are roots of this equation, so fa equal to 0 and fb equal to 0. So third condition, fa equal to fb equal to 0. These three conditions of polynomial equation for Rawls theorem are satisfied. Then the conclusion of Rawls theorem, there exists a point x equal to c belongs to open interval AB, where f dash c equal to 0, that is c is a root of f dash x equal to 0. Thus, between any two roots of a polynomial equation fx equal to 0, there is always a root of its derivative f dash x equal to 0. Here we take some questions on Rawls theorem. Nature of problems on Rawls theorem. Generally, two types of problems are formulated on Rawls theorem. First, applicability of Rawls theorem. Second, verification of Rawls theorem. Third may be taken as based on algebraic meaning. In both the situation, applicability or verification, we first check the three conditions of Rawls theorem. In doing problems, we use some result directly, like addition, subtraction, multiplication, division of continuous and differentiable function. Again continuous and differentiable. Second, We use directly result relation between continuity and differentiability. Differentiability implies continuity, not differentiable, may or may not continuous. Continuous, may or may not differentiable, not continuous, not differentiable. We have already used this result in previous chapter. Next, polynomial function, exponential function, sine function, cosine function, and constant function everywhere continuous and differentiable. But cosec, sec, tan, cot, logarithmic function continuous and differentiable in its domain. Also, piecewise defined function like greatest integer function, fractional part function, least integer function, these are everywhere continuous and differentiable except integral points. We also use a direct basic differentiation. If derivative of a function f dash x equal to tends to infinity or minus infinity at any point, then f is not differentiable at that point. Now we take problems on Ross theorem. Your first question is, check the applicability of Ross theorem. Function is fx 2 plus x minus 1 whole to the power 2 by 3 on the interval close interval 0 to 2. We have to check first three condition for continuity, differentiability and functional value at any point. Clearly function is continuous in closed interval 0 to 2. For each and every value of x between from 0 to 2, we get fx has definite real value. So function is continuous. So limiting value equal to function value at each point. So function is continuous. Second, derivative condition, differentiability condition. Here we use direct differentiation f dash x equal to derivative of 2 0, derivative of d by dx x to the power n, nx to the power n minus 1. So d by dx x minus 1 whole to the power 2 by 3 equal to 2 by 3 x minus 1 whole to the power 2 by 3 minus 1. This will give 2 by 3 1 upon x minus 1 whole to the power 1 by 3. Here, if denominator becomes 0, then f dash x becomes undefined. So at x equal to 1, function has derivative has f dash x has no real value, so which is not finite at x equal to 1, so does not exist finitely, that is not differentiable at x equal to 1. Here we do the continuity check by this step. We know differentiability implies continuity. Here f dash x is defined everywhere except x equal to 1. So differentiable in 0 to 1 union 1 to 2. Differentiable in 0 to 1 union 1 to 2. Here open interval on 1. Differentiability implies continuity. This implies also continuous in this interval. Here we check only continuity at x equal to 1. Clearly f at x equal to 1, f1 limiting value at x equal to 1 and left hand limit at x equal to 1, right hand limit at x equal to 1 both will be here 2 and limiting function value at x equal to 1 2. So function is continuous at x equal to 1. We can do this step through differentiability. Here second condition of Rolle's theorem is not satisfied. Therefore, Rolle's theorem is not applicable for the given function in the given interval. We take next question. Are the condition of Rolle's theorem satisfied in case of function fx equal to cos 1 by x on closed interval minus 1 to 1? Here fx equal to cos 1 by x. We know in previous chapter fx equal to sin 1 by x, fx equal to cos 1 by x have discontinuity of oscillating type. Clearly, this function is discontinuous at x equal to 0. Oscillating type discontinuity means this function oscillates between two finite number minus 1 to 1. Not continuous means not continuous at x equal to 0. This implies not continuous in closed interval minus 1 to 1. Also not differentiable in open interval. In criteria of Rolle's theorem, we take closed interval in AB and open interval in AB in case of differentiable second condition. F of minus 1, functional value of endpoint, cos of minus theta cos theta. So f of minus 1 and f of 1 both are equal. Here first and second condition of Rolle's theorem are not fulfilled. So answer is no. The third question. Fx equal log x square plus ab upon a plus b into x on interval closed interval ab where a and b are positive number. Here we have to check applicability of the function and also verify the Rolle's theorem for the given function. First of all, fx equal to log x square plus ab a plus b into x. We rewrite the function log x square plus ab minus log x minus log of a plus b. Here we use properties of algebraic operation on continuous and differentiable function. Since logarithmic function is continuous and differentiable in its domain, here fx being sum or difference of continuous function, so it is continuous in closed interval AB, differentiable in open interval AB. Here function is the sum or difference of continuous and differentiable function for positive x. So it is also continuous on its subset closed interval AB, differentiable in open interval AB. Also fa a square plus ab a plus b into a, again a square plus ab, so equal to log 1 equal to 0. F of b means log b square plus ab a plus b into b means b square plus ab. So fa plus fb both equal to 1 0. Here all the three conditions of Rolle's are satisfied. So Rolle's theorem is applicable for the given function in the given interval. Second easy method may be f dash x. We know dy dx log x 1 by x, dy dx log of phi x 1 by phi x. Here f dash x equal logarithm dc of this 1 upon x square plus ab, and again into dc of x square plus ab 2x plus 0, dc of x square 2x log x 1 by x and log a plus b constant, so 0. After simplification This becomes 2x square minus x square minus ab upon x into x square plus ab, x square minus ab upon x into x square plus ab. Here f dash x becomes undefined if x is 0 or x is negative. X is 0. Here we have interval, close interval a to b, or here a and b are positive number. Here this expression is finite for all positive x. For all positive x, so f is differentiable for all positive real number x. Since differentiability implies continuity, so continuous for all positive x. Here positive x means open interval 0 to infinity. Its proper subset is this interval. So f is continuous in closed interval ab, differentiable in open interval ab, and fa equal to fb equal to 0. Therefore Rolle's theorem is applicable. If question demand applicability of Rolle's theorem and verification of Rolle's theorem, we know conclusion of Rolle's theorem involves derivative at a point. If these two, applicability and verification, both are required, this method should be preferred because ultimately we will have to find derivative at some stage. Third method may be here fa equal to fb equal to 0. We already saw above. fa equal to fb equal to 0. Right hand derivative r f dash x limit fx plus h minus fx by h tends to 0. fx plus h log h square x plus h whole square plus ab upon a plus b into x plus h minus fx means this log expression divided by h. After calculation, this will give x square minus ab upon x into x square plus ab. Replacing h by minus h, we get left hand derivative at x, L f dash x limit h tends to 0, fx minus h by minus h minus fx. This will again after calculation x square minus ab by x into x square plus ab. Here in both situation, this is finite for all positive real number, this also finite for all positive real number. These two are same, so function is differentiable for all positive x. So continuous for all positive x. We have continuous in closed interval ab, differentiable in open interval ab, fa equal to ab, hence the result. Here second part of the question is verification. Verify the Rolle's theorem. Here f dash x square minus ab upon x into a plus b. We have a statement for the Rolle's theorem, continuous in closed interval ab, differentiable in open interval ab, fa equal to fb. Here these three conditions are fulfilled for the given function. So there must exist at least one value of x equal to c in open interval ab, where f dash c equal to 0. So we let f dash x equal to f dash c equal to 0, where c is a value of x. This implies c square minus ab upon c into a plus b equal to 0. c square minus ab equal to 0, c square equal to ab. C square equal to ab, so c equal to under root ab. This is the geometric mean of a and b. So c is the geometric mean of a and b. C is the geometric mean of a and b. So c must lie between a and b. C belongs to open interval AB. Thus there exists at least one value of x equal to c belongs to itna such that f dash c equal to 0. Here, if c does not belongs to open interval AB, then we say that Rolle's theorem is not verified, because here c belongs to AB, Rolle's theorem is verified for the given function in given interval. The fourth question, verification of function. Here fx equal to x cube plus x square minus 4x minus 2. Notice that here no interval is given. First of all, we see fx is a polynomial function, so it is continuous and differentiable everywhere. Since interval is not given, so first we think for interval. For this, taking fx equal to 0, 2x cube x square minus 4x minus 2 equal to 0. By inspection, we put here x equal to 1 minus 1 2 minus 2 root 2 minus root 2 etc. We see that x equal to root 2 will make LHS equal to RHS. So x square equal to again 2 x square minus 2, it is a factor. Here making x square minus 2 factor in this term, taking out 2x outside, x square minus 2, and adjusting 2x cube minus 4x, we have already minus 4x, remains here 2 term x square minus 2, taking plus 1 outside x square minus 2, so 2 factor 2x plus 1 x square minus 2 equal to 0, x equal to minus half minus root 2 2. We have three values of x here on a number line. We f of root 2 equal to 0, f of minus root 2 equal to 0. So f of root 2, f of minus root 2 both equal to 0. So we can take interval minus root 2 to 2. Function is everywhere continuous differentiable. So continuous in its proper subset, minus root 2 plus root 2. Always care here. In case of continuity, we take closed interval. In case of differentiability, take open interval. And conclusion, C for conclusion in open interval. So continuous in closed interval, differentiable in open interval, and f of minus root 2 equal to f of root 2. Since all the three conditions are satisfied, so there must exist at least one value of x equal to c. X belongs to open interval where derivative vanishes. So here we assume f dash c equal to 0. 6c square dc, 6x square plus 2x minus 4, cancelling common factor 2, 3c square plus c minus 2. This equation gives c equal to minus 1 2 by 3. If both these values do not belongs to this interval, then Rolle's theorem verification fails for Rolle's theorem. But here minus 1 and 2 by 3, minus 1 and 2 by 3 both belongs to this interval. If any one belongs to, at least one of the two belongs to this interval, then Rolle's theorem may be verified. Here both value of c belongs to this. If assuming this value will not belong to this interval, and this value belongs to this interval, verification will be assured. So, if interval is not given in question, we find first thing for interval, we find fx equal to 0 and value of x are find in such a way, and b here different possibility, minus root 2 to minus half to root 2, minus root 2 to root 2. So fifth question is fx equal to x minus a whole to the power m, x minus b whole to the power n on closed interval ab. We have to verify Rolle's theorem here. A binomial of mth degree, binomial of nth degree, after multiplication, fx is a polynomial of m plus nth degree. Since fx is a polynomial, so continuous and differentiable everywhere. This implies continuous in closed interval ab, differentiable in open interval ab. At x equal to a, this becomes 0. At x equal to b, again 0. So fa equal to fb equal to 0. Thus all the three conditions are satisfied. Now we do for verification part. First differentiate fx. X minus b d by dx power function x to the power n and x to the power n minus 1 we use here. X minus b whole to the power n, dc of this m, x minus a whole to the power m minus 1. Again first factor x minus a whole to the power n, dc of second n into x minus b whole to the power n minus 1. Here x minus a whole to the power m minus 1 and x minus b whole to the power n minus 1. Taking out common from both the terms, we have m into x minus b plus n into x minus n bracket, x minus a m minus 1, x minus b power n minus 1, and this becomes m plus n into x minus mb plus n. Let f dash x equal to 0. Let f dash x equal to 0, and after solving this equation, if at least one value of x be a part of open interval AB, then Rolle's theorem will be verified. So f dash x equal to 0, this is equal to 0. Here x minus a m minus 1, x minus b n minus 1, these two factors are not equal to 0, because if this equal to 0, x equal to a, x equal to b, here a and b are different, so this two factor not equal to 0, so only this factor bracketed expression will be 0. This will give x equal to mb plus na upon m plus n. We know internal division formula from coordinate geometry. A is a point having coordinate a0, b is a point coordinate b0, and p is a point which divides this line segment AB internally in the ratio m is to n. Then coordinate of b will be mb plus na divided by m plus n. This is internal division point of joining line this point to this point. So here x equal to mb plus na by m plus n belongs to open interval AB, being a point which divides AB internally in the ratio m is to n. So we see here Rolle's theorem is verified. Okay.